Hey guys, it's Genius Tutorials 2015 here. We're going to be doing dynamics, UCM, and gravity, or uniform circular motion and gravity problem bank today. So let's start off right with question one. Question one is says a torque of 58 Newton meters is produced using a wrench of length 30.35 meters to loosen a nut. Calculate the minimum force exerted at the end of the wrench. So all we have to do is set up our equation of torque, or tau, is equal to force times the radius times sine of theta. In this case, so in this case, the force and the sine theta is going to be the angle. Theta is going to be the angle between the radius and the force. So in this case, it happens to be 90 degrees because you have the wrench and the force pushing on it. So here's the radius and here's the force. They're going to be at a perpendicular angle. So sine of 90 is just going to go to 1. So it's really just going to be just that F times R. So it says our torque is 58. That's going to be equal to the force times the radius, which it says is 0.35 meters. So we get that our force is equal to, our force is going to equal 165 newtons approximately. So that's number one. On to number two. Part B. On number one, calculate the angle of a force of 662.85 newtons must be applied to the middle of the wrench to produce a 58 Newton meter torque. So it tells us that the torque again is 58 meters to produce a force of 662.85 newtons, and it says to the middle of the wrench. So our radius is now cut in half. The radius is always the distance from the force to the point of rotation. So in this case, it's going to be 0.35 over 2, and then sine of theta. So we're looking for theta in this case because it says there is an angle between them. So theta is just going to be the sine inverse of 58 over all of that, 662.85 times 0.35 over 2. So sine inverse of all of that, we're going to end up with, one sec to type it on the calculator. We're going to end up with about 30, it's going to be a 30-degree angle. So theta is going to be 30 degrees. Next, number two, we've got coefficient of static friction between the road and the tires on a Formula 1 car is 0.6 during a Grand Prix auto race. Calculate the speed that will put the car on the verge of sliding as it rounds a level curve of 30.5 meter radius. So this is going to be UCM. So there's a so we have a circle with a radius of, there's a radius of 30.5 meters, so when we do summation of forces, always do summation of forces even for UCM. The only thing different is the net force is the centripetal force. So the total net force is the centripetal force, making the acceleration the centripetal acceleration. And our formula for centripetal acceleration is v squared over r. So we get net force equals mv squared over r. So then we just calculate the net force like always. The net force holding the car inside this circle is going to be the force of friction on its wheels. So we're going to do force of friction equals mv squared over r. Force of friction is just mu times the normal force, and the normal force in this case is going to be equal to its weight, or mg. So we're going to have mu mg equals mv squared over r. M's will cancel, the masses will cancel, and speed, we're calculating speed. Speed is just going to equal mu r, or mu rg square root. So you can just plug in the values and you get a velocity of times the radius of 30.5. You're going to get about 13.39 meters per second. So that's that. Next one, number 3, an air puck. So there's an air puck with a mass with a certain radius spinning in a circle on a frictionless horizontal surface. Other end passes through a hole held with a mass hanging from that string. If the mass remains in equilibrium while the puck revolves, we have to find each of these. So the magnitude of the force acting on the puck that maintains circular motion. That's basically asking for the centripetal force, which we always say is the net force. So in this case, if everything's in equilibrium, the mass isn't moving down. So the puck, you're going to have the puck with, we're going to draw two different FBDs. You have a puck with a weight down, a normal force up, and a tension, which is the centripetal force in this case, going in. Then you have a big mass with a separate weight going down and the tension holding it up. Tension is an internal force, so it's going to be the same throughout the wire, and since it's equilibrium, the weight's going to be equal to this tension because it's not moving. Therefore, we can say that net force equals mass times acceleration. So on that puck, that tension is the centripetal acceleration. It's going to equal. It's going to be equal to the weight in this case. As you can see, tension equals weight. So this is the weight of the big mass, of course. The big mass is 1 kilogram, so multiply that by 9.8, and you should get 9.8 newtons. Then it's asking to find the tangential speed of the puck, so we're just going to say that 9.8, which is the centripetal force, or the tension in the rope or the string, is equal to mv squared over r from our equation from before, and we can just multiply that to say that a radius is 1, so 9.8 divided by the mass of that puck, which is 0.025 kilograms, square root that to get the velocity. Excuse me. And we get a velocity of about 19.8 meters per second. Next, how many complete circles does the air puck make in 1 minute? So we can say that's it's traveling around in 19.8 meters per second, and each revolution, the distance it goes in that amount of time is the circumference of the circle, or 2 pi r. In this case, r is 1, so it's just going to be 2 pi. 2 pi meters is the distance it goes at that speed. So we can say so we can say that the time it takes to go around the circle one time, we can say that distance equals velocity times time. So the time is going to equal distance over the velocity it goes, which is going to be equal to 2 pi over the 19.8. And that's going to equal 2 pi divided by 19.8. That's going to give us 0.317 seconds. Now it's asking in 1 minute how many revolutions we can make. If that's how long it takes us to make one revolution, we can just do 60 seconds divided by that much time, and we get 189 revolutions. So we're going to have 189 revolutions. Alright. Question 4 is asking a car is traveling at a constant speed, safely negotiates a frictionless bank curve. Bank curves are basically curves that are lifted up at an angle, as shown in the figure. And it's asking to calculate the speed of the car when the road is banked at 20 degrees. And the radius of its path is 50 meters. So we can draw the FBD of the car. So now we have, obviously the car is going to have a weight down. Now it's going to have a slanted normal force instead of vertical. So it's going to have a slanted normal force, and it's banked at 20 degrees. So this normal force is going to be offset from the vertical by 20 degrees. And if we extend this normal vector down, that's also going to be the same angle. So there we go. And we can say that there is, and we know that the curve is frictionless, so there's no friction along the curve. So it's asking, the speed of the car if it's banked at 20 degrees, and we know the radius is 50 meters. So we can say that on the net force equals mass times acceleration side, we know that the mass times acceleration is just mv squared over r. So we can get that to equal, we know that the mass is going to cancel in the end with the force side, so we're just going to get the centripetal acceleration, which is just the v squared over r portion. And we know the v squared over r is going to be, and we're looking for the v squared, so we know it's going to be mv squared. Basically, we know what the r is, that's the only thing we know, which is 50 meters. That's going to be equal to a net force. Now, the net force is always the centripetal force pointing towards the center. So that's simply going to be the, if we take the, so if we know that this component right here, our car is not accelerating along the bank curve, so we know that this normal force is going to be equal to this weight component. So this normal force is equal to the weight cosine of 20. Cosine of theta, we're going to say normal force equals weight cosine of 20 degrees. And so if we want to find, this normal force has a horizontal component, which is what our centripetal is going to be, because it's always pointing towards the center. So we can simply say that now we have the normal force, we have an angle, we're trying to find the opposite side, and we have the hypotenuse. We can say that sine of 20 degrees is going to equal the opposite side we're looking for over our normal force, which we said was weight cosine of 20 degrees. So we can say that that side that we're looking for, which is going to be our centripetal force, is going to equal weight cosine of 20 times the sine of 20 degrees. So that's going to get us the weight of the car is just going to be mass times, this is just going to be mg. So we know that this m, once we set that equal to over here, we're going to set x equal to over here. We know that the m's will cost out, so we don't even need the mass for this problem. So we just multiply by the acceleration due to gravity, and that's simply, and from that I got 3.149. It's going to equal v squared over 50. So if we multiply that side, both sides by 50 and square root that, we get that the velocity, well, I got 12.55 meters per second. It's gonna be, that's probably because of rounding, so. 287, 1 second. This would also be the same as saying x would equal the, or tangent of 20 degrees would equal opposite over the weight. So, saying 9.8 equals, or 9.8 times the tangent of 20 degrees is going to equal that, multiplying that by 50, and then the square root of that. Yeah, so, sorry about that, so scratch this way. It's making it more complicated. Just, what I did here was tangent of 20 equals x over w, because this component is going to be equal to this component right here. So, you know, this is the weight, so you have an adjacent side, you have an opposite side, and you have an angle. So tangent of this angle is opposite over adjacent. This side is the x, yeah. And and plugging that in using the corrected value here, which was 3.57, that gets you a v of 13.35 meters per second. So there you go. Next up, number 5, we have 2 skaters holding opposite ends of a spring spinning of a spring constant of 650. They're spinning in a circle, and frequency of revolution is measured to be 0.85 hertz. We have to find the mass of the skaters. So they're identical skaters. So right now they're spinning in a circular motion. So their centripetal force is the force on the spring. We know that a force on a spring is equal to kx, so the spring constant and the displacement of the spring. And so their frequency is 0.85 hertz, and frequency is the inverse of period. So period is equal to 1 over frequency. Period is the time it takes to make 1 revolution. So if we know 1 revolution, the distance is 2 pi r, and divided by the velocity they're going at is going to equal, is the period, is going to equal 1 over their frequency. So we can say that their velocity is equal to, their velocity would be equal to 2 pi r times the frequency. So that's going to come out to be 2 times pi times their frequency of 0.85. We don't know what the r is, so it's just going to be 5.34 r. So that's their velocity. And it's asking to find the mass of the skaters. So the mass of the skaters, so if we do net force equals mass times acceleration, net force equals mv squared over r. If we find the mass of one skater, so it's going to be the spring constant times the displacement, or the force on the spring, which is the centripetal force, equals m. We said that their v was 5.34, so times 5.34r, make sure we square that, divided by r. And so here we have, and so we said that the K was 650. So we have 650, and if you notice the X is the displacement of the spring, and in this case the displacement of the spring is just the radius. So it's going to be 650R equals M times what 5.34 squared is 28.52. And you see r squared over r is just r. So you see that the r's will cancel simply. So we can find m. M will just be equal to it's actually going to be 2r, the displacement of the spring, because the spring was initially at, close together, and you actually displaced it a distance 2r, r this way and r this way. So actually multiply this side by 2, and now you get an answer that is 45.6 kilograms. Yeah, so make sure you multiply that displacement of the spring by make sure the displacement of the spring is 2r, not just r, because it went in both directions. So that's going to be the mass of each skater. Next question we can do on this side. George of the Jungle has a mass of that, swings on a vine. Calculate the tension of the vine when George is moving at 2.4 meters per second and the vine is vertical. So he's swinging on a vine, here's the vine, he's swimming back and forth, but find the tension in the vine when he's vertical. So we're just going to draw an FBD. So he has a tension going up because the vine is pulling him up and the weight's pulling him down. So the tension is allowing him to stay up. So again, net force equals mass times acceleration. Now centripetal force is the same thing as net force. So the net force in this case is tension minus weight, since they're in opposite directions. And that's going to equal mv squared over r. So it's asking to find the tension in this rope. Just add the weight to the other side, mg plus mv squared over r. Plug in your variables and you'll get an answer that is along the lines of, so v squared is 2.4 squared divided by the radius at acceleration due to gravity and multiply by his weight of 75 kilograms, and you get a tension of 801 newtons. Number seven is talking about a radius of curvature of a loop-to-loop roller coaster at 12 meters. At the top of the loop, the force that the seat exerts, so you have a loop. Here's a loop. We'll just use a circle as a loop. At the top of the loop of this roller coaster, the force that the seat exerts on the passenger of mass m is 0.4 mg. So that's basically this force right here is 0.4 mg. Asked to calculate the speed of the roller coaster at the top of the loop. So we can do a summation of forces for this as well. The seat is exerting a normal force down, and there's also a weight down as well. So in this case, net force equals mass times acceleration. Our net force is normal force plus weight equals mass times v squared over r, because this is centripetal. Normal plus weight equals mv squared over r, since this is a centripetal acceleration. So in order to find the speed of the roller coaster at the top of the loop, we know that it's a 12-meter loop and he has a mass of m. So it says that at the top of the loop that the seat exerts 0.4 mg on him. So that's the normal force. The seat is a surface exerting a force, a normal force on the passenger of 0.4 mg. The weight is of course simply mg always, and that's equal to mv squared over r. The m's will cancel from all these equations. You have 0.4g plus g gets you 1.4g times the radius of curvature, which was 12 meters, equals your v squared. Solving for v will get you 1.4 times that times 12 will get you 12.83 meters per second. Last couple problems here. Number 8, switching to blue paper. Number 8, asking about during a solar eclipse, you have the moon, the earth, and the sun in the same line with the moon between the earth and the sun. So calculate the force exerted on the earth by the sun. So using our gravity equation, we have force due to gravity. Of course, force due to gravity is equal to our big G, gravitational constant, times the mass of one, the mass of the other, over their distance squared. So, of course, this equation is the equation for all gravitational attraction. We use little g equals 9.8 for things that are near the surface of the Earth. And that's for all things near the surface of the Earth because the radius is of the Earth is very big compared to the distance of the Earth that we use. That's why we say on or near even. But once this radius gets to an amount that starts significantly changing this answer, we cannot use 9.8 as the acceleration due to gravity. It is not constant. So, the force exerted on the Earth by the sun, that's just going to be big G times the mass of the Earth times the mass of the sun divided by the distance from the Earth to the sun squared. So if you do that all out, that comes out to be 3.52 times 10 to the power of 22 newtons. So that's how you do that. I'm not going to plug them in. They give you the constants on the sheet right here, so you can just plug in the masses, plug in G, and plug in the distance squared, and get your answer. Same thing for moon by sun and moon by earth. You can calculate those as well. So yeah, number 9. On Apollo missions to the moon, the command module orbited at an altitude of 110 kilometers above the lunar surface. Calculate the time it takes for the command module to complete one orbit. So you have the command module orbiting an altitude of 110 kilometers. So here's the moon, 110 kilometers going all the way around. So it's asking the time it takes for the command module. So this is a uniform circular motion. So you have the force of gravity, which is what's keeping it in, force of gravity. So basically the weight of this satellite at this distance is equal to mv squared over r. Now you can, for the weight, you can make sure you can use the gm1 m2 over r squared equals mv squared over r. Now the mass, this is the mass of the satellite, and that'll cancel with one of these masses, so you'll just be left with big G mass of the moon over the distance to the center of the moon over v squared over r. So you can use that to find the velocity, and once you find the velocity, you can use the equation d distance equals v times t, or t equals distance over velocity. So once you find the velocity, the distance is just going to be 2 pi r over the velocity. And so you can just, again, plug in these values. So that's how you do that. And finally, for number 10, there's a point between the Earth and the Moon where the gravitational effects of two bodies balance each other. Calculate the distance from the center of the Earth. Calculate the distance from the center of the Earth to this point. So, from the center of the Earth. So, basically, if you have the Earth, the Moon, and there's some point, it's obviously going to be closer to the Moon, because the closer something is to an object, the stronger the gravitational force. If it was an equal distance, the Earth would obviously have a stronger pull, because the distances are equal, but the mass of the Earth is greater. So the masses of the objects and their distances come into play. To counteract the mass of that planet Earth, you're going to have to put it a greater distance, weakening the force to balance out. So here's the distance. And so the force attraction between these two is going to be equal to the force attraction between these two. So gravitational constant, so force of gravity is equal to g m1 m2 over r squared equals g m1 m2 over r squared. In this case, g's will cancel. One of the masses will cancel because that is the mass of whatever the object is. But the other masses don't cancel because one is the mass of the Earth and one is the mass of the Moon. And then your distances also don't cancel. Those are also different. So if you do this, the distance between the Earth and the Moon, you would have to say distance between the Earth and the Moon is, it says 3.82 times 10 to the 8. So one distance, so this whole distance is that distance. We're trying to find the distance from the center of the Earth. So we can say 1 is x, 1 is going to be that distance minus x. So we can say one of them is x squared. So we're going to say from the Earth, it's x squared. From the Moon, it's going to be d minus x squared. You know what d is, you know what the masses are, you just simply cross multiply and find out what x is from this equation. You should get x equals 3.44 times 10 to the 8 meters. Should get 3.44 times 10 to the 8 meters from that, from the Earth. So that's number 10. So that's UCM and gravity. Make sure, number one thing, every time you're doing UCM and gravity problems, you always, first of all, always want to make a free body diagram, draw your forces, draw the vectors of the forces, summation of forces. Always draw that free body diagram. And secondly, always write out a summation of forces equals mass times acceleration. Every problem will always stay true to this equation. This is Newton's. This law stays true always in all situations. So make sure you always follow this law. Free body diagrams and EF equals mass times acceleration. So make sure. Hope that helped, guys. That was UCM and gravity. Until next time, see ya.